Okay. So the third one was this master method. It can solve only a specific type of recursions. Tn equal to a Tn by b. So a, b are constants which are greater than equal to 1. So what we will do is we'll compare Fn with n to the power log b by a. If Fn is smaller than this quantity, then the solution is Tn theta n to the power log b by a. If it is equal to some polylog factors, let's say it is n to the log p by a into log n to the power k, then Tn will be theta n to the power log p by log n to the power k plus 1. And if it grows n to the power log p by a, then this Fn term will dominate the solution. So Tn will be theta. So let's say I do a recursion like this. Using this theorem, what will be the solution to this recursion?
L.
So what is A here? 4. B is 2, right? So here log 4 to the base 2, right? So it will be 2. So theta of n to the power log b by. So that is theta n. Right? For this example, Tn equal to 4t uh, n by 2 plus n square. Sorry, this should be the opposite. It should be dt n. Right? This was the recursion we saw in integer multiplication. So what is the solution here? So just applying this, right? B is 4, A is 2. So this will be n square into K will be 0 here, right? So overall the answer will be theta n square log. What about the third? What is the solution here?
of n cube.
Yeah, because Fn grows bigger than n square. So Fn is n cube, so Tn is required. Okay. So yeah, so this is the end of the analysis part. Basically, if you have an algorithm you have designed, you will know how to analyze this, construct some recursion, and use it by any solve that recursion by any of the three methods, either substitution method, recursion tree method, or this ready-made theorem which we have master method. Okay. Most recursions can be solved using master method, but there will be some places where you have to apply the recursion tree method. Okay, so now we'll move to more interesting stuff, which is the design part, algorithm design. And the first technique which we'll see is divide and conquer. So you have some difficult problem to solve. What it will mainly follow these three steps. Divide step, which is dividing the input into several smaller fragments. Then there will be some conquer step, to solve the problem on the smaller fragment. So the original problem may be difficult on the entire input, but on a small fragment of the input, maybe it is easier to solve. So you solve the problem on the smaller fragments. And finally, you combine the solution to the smaller fragments to yield the solution to the original. Okay? There is three steps: divide, conquer, and combine. And we will see how to apply this technique for solving various problems. Okay? So our first example is with binary search. So what is the input? You are given a sorted array. So you know that the array of is an array of numbers, and you know that it is already sorted, and you are given some element. It may be or may not exist inside this array, and if it does not exist, then you output that this element does not exist. Otherwise, you find the position of this element in this array. Okay, is the problem clear? So for instance, we have these elements 1, 3, 4, 6, 8, 11, and 12. Okay? And find 8 is the question. Okay? So in this case, at zeroth location, you have 1. Uh, First location, you have 3. Second location, you have 4. Third location, you have 6. And fourth location, you have 8. So you should output 4 in this case. Okay, so how will you solve this problem? So one trivial algorithm is check for every element from the starting element of it and return the maximum. So in this case, you start from the first element, it is 1. Check whether 8 equal to 1 is not. Then check whether 3 equal to 8. Check whether 4 equal to 8, 6 equal to 8. Then finally you will come up with this element 8. And then you have a match and output the location of this element. Right? The algorithm clear? So we check for every element from the starting element of it and return the match. And if the array total has n elements, so this element could be anywhere in the array. It could be the first element, it could be the last element. So in case it is the last element, then you will require order of n time. Okay? Big O of n time. So the running time of this algorithm is big O of n. Okay? And now the question is, can we do better than this trivial algorithm? Can we get a small O of n, strictly sublinear? Okay. Can we get a root n algorithm, or can we get even smaller? Okay. Yeah. So any ideas for smaller and bigger? Let's say you have this array here. This array has 7 elements. What is the so we saw one algorithm which requires going over all the 7 elements and checking whether 8 is one of them. So what you are allowed to do here is you can compare the target element with individual elements in this array. So do you need to compare with every element in the array or is there something better? So you have to make use of the fact here that this array is sorted. If this array was not sorted, then obviously you couldn't have done it. Any guesses regarding what can be the so initially there are n options where this element can be, assuming the size of the array is n. Now using just one comparison, can you reduce this uh, sample space of array? The question is clear, right? So there are seven elements in this array. Let's say I choose the fourth element, which is the central element, 6. So there are three elements smaller than that, three elements larger than. So I compare 8 with 6. Okay. So 8 is larger than 6. So if 8 existed in this array, it couldn't have been to the left side of 6 because all these elements are smaller than 6. Right? So the only option is to the right side of this array. Okay? So initially I had seven elements to choose from. Now I have only three. Okay? So the sample space is reduced by half. Okay? Now what will be the next comparison you have to make? I have three elements, 8, 11, 12. So you'll do the same thing again. You'll pick the central element. In this case, it is 11. There is one element to the right, one element to the right, left. So 8 is smaller than 11. So obviously it has to be on the left side of 11. And you just check that element. and it exists, and so you can output whatever is the position of the cell. Okay. Simple enough algorithm. Now, what is the running time? So this is our divide and conquer strategy. Check for the middle element. Recursively search one subarray. Either it is to the left of that middle element or to the right of middle element. And combine is trivial because you just have to check one subarray. There is no combine happening here. So this is our pseudocode for this. Low is the index of the first element, high is the index of the last element, and k is the element which we want to search, and a is our array. If low is greater than high, then obviously there is nothing to do, return no key. Else we'll look at the middle element, which is low plus high divided by 2. If k equals the middle element, then you return that mid is the position of that element. Else if k is larger than this element, then that element is to the right of the middle element. So it can either be between mid plus 1 or high. Or the other option is that k is less than the middle element. So it had to be to the left of the middle element. And we do binary search on a low mid minus 1. Okay. So now how will you analyze this algorithm? So the first step is you have to construct some recursion here. Let Tn be the time taken for binary search in an element array. Right? In every step, you are doing one comparison that will take theta of one time. Plus, and finally, the search space got reduced by half. Okay, okay, today is a holiday. But anyways, let's continue. Okay, so should we continue or should we stop here itself? Okay, we'll continue then. So here Tn equal to Tn by 2 plus theta of 1, right? So you know how to solve this recursion, right? You can use your favorite method. In this case, I think recursion tree method will work the best. So at every time you are dividing by 2 and otherwise it just a constant. So all this recursion will run for how many steps? If n is equal to 2 power k, Yeah, order of login. Or you can say theta of login. Okay. Okay. So we have theta of login time algorithm for this problem. Very on binaries. Now, can you beat this login term? And you get a, let's say, theta of login. So basically, you want to show a lower bound of omega log. So how will we prove a lower bound of omega log? So that is using this technique of decision. Okay? So what we do here is we check for the middle element. If it is less than the middle element, then we check for some other element. If it is larger, then we check for some other element. Again, you check whether it is less than or greater than. If it is less than, you check for some other element. If it is greater than, check for some other element. And finally, you do all these sequences of comparisons. If it is less than, then you declare that it is the first element. If it is greater than, you can declare that it is the second element. So all these sequences of comparisons, they form a tree. Right? And in this tree, and we want to lower bound the number of comparisons. And the leaves of this tree, they are the various different indices possible for this. Okay? So if an array had size 8, it will have 8 many leaves. And we want to bound the height of this tree, which is the distance from the leaf to the root. Okay? And if you are given the number of leaves, which is n, what can be the maximum height or minimum height? Okay. So for that you can use some inductive argument here. So if the height is h, then the number of leaves is 2 raised to h. Right? Because initially at the root you have just one element, then you have two elements, then you have four elements, and there are 8 elements at the last. So you can guess that the number of elements is 2 power h. And using an inductive argument, you can actually show that 2 power h equal to the number of. In this case, if the number of leaves is n, then h has to be at least log n. Right? The number of comparisons will be at least log n if you are allowing only comparisons. Yeah. So this is how we generally show lower bounds in this model. Okay. So next example using divide and conquer is that of powering a number. Let's say we have two numbers, a and n. You want to output this a to the power n. Each multiplication you can assume that it takes constant time. Right? So here there is one simple algorithm for powering the number. For I from 1 to n, you just keep on multiplying by a. Right? This variable a will hold the value of a to the power n. And how many multiplications you are doing? There are n many multiplications. So the total running time will be theta of. Okay? This is the naive algorithm. Now you want to beat this using dividend. So how will you use divide and conquer to compute a to d? We want to compute ADTN. So here is one idea. Split a to the power n as a to the power n by 2 into a to the power n by 2. Okay? If n is even, obviously then it can be split. If n is odd, then it's just a into a to the power n by 2, a to the power n by 2. Now the trick is that you just have to compute this a to the power n by 2 once and then square it. Okay? And overall it will be just Tn equal to Ten by 2 plus 1. Okay? So again you get a log n diagram. And in fact this is optimal, but the proof is very long. So even if you allow additions or subtractions, you can't do much better than long. Okay. So this is about integer power. Then there's one more example comes from integer multiplication. This we already saw in the first class and maybe you have coded it as well. There are given two n-bit integers, a, b in base r, and you want to output a dot b. Okay. So let's say you are given two 4-digit numbers and you want to split it into 2-digit numbers, x1, x0, y1, y2. So it is hard to multiply to 4-digit numbers, so we split it into two 2-digit numbers. This is the first half of the number, x1, and x0 is the second half of the number. And you split it this way and find the product of x dot y. Okay. So x1 y1 r raised to l, x0 y1 plus y0 r raised to l equals x dot y. So you require 4 multiplications this way. But then we saw this trick that you can split it into x0 plus x1, y0 plus y1, and subtract it from the two initially computed multiplications. So you can do it using just 3 multiplications. Okay. And we saw how to solve that recursion, and solution is some n to the power 1.5.
Sorry, excuse me, sir.
Yeah.
Sir, isn't it holiday today? Because it was in
Yeah,
academic.
yeah, I didn't know that. So anyways, I have taken this class. We'll repeat it
Okay,
in the next class.
okay, sir. Thank you, sir.
Yeah, so I think we will stop here now. Do the same again next class along with some additional things. Okay. So if there are any questions, okay, if there are none, we'll stop here. Meet on Thursday. Thank you.
Thank you, sir.